Chapter 3, Chemical Equilibrium, Class Life Sciences. Part 7, Composition of a System at Equilibrium. At the end of this session, students should be able to define the degree of conversion alpha, determine the composition of a system at equilibrium in terms of X and alpha. Composition of a system at equilibrium 7.1 in terms of X. What is meant by X? We denote by X the quantity reacted, that means disappeared, of a reactant at equilibrium starting from the initial amount of this reactant. Composition in mole from the number of moles. X is the number of moles of reactant A, for example, disappeared at equilibrium for the general reaction AA plus BB gives CC plus DD. At T equals 0, the initial number of moles are N0 for A, N0B for B, and 0 for C and D. X is the number of moles of reactant A disappeared or decreased at equilibrium or at instant T. Then reactant A, the variation is minus X. For B and C and D, it depends on the stoichiometry of the reaction. According to the stoichiometry of the reaction AA plus BB gives CC plus DD, we can write number of mole of A reacted over A equal number of mole of B reacted over B equal number of mole of C formed over C equal number of mole of D formed over D. Now, number of mole of A reactant is X. Then the relation becomes X over A equal number of mole of B reacted over B equal number of mole of C over C equal number of mole of D formed over D. If you want to calculate the number of mole of X of B reacted in terms of X, the number of mole of B reacted equal B times X over A. Then B decreases by an amount equal B over AX minus because it decreases. For the product C, it increases plus an amount equal C times X over A plus C over AX, and the same for the product D, it increases plus D times X over A, then plus D over AX. In general, if we consider X is the amount of reactant A disappeared, then for the other component of the reaction, we divide the stoichiometric coefficient of the reactant that we should calculate its amount reacted by the stoichiometric coefficient that we consider it decreases 1x, B over A, times the amount X. For the product, the same, C over A X, D over A X. Then at equilibrium, number of mole left for the reactant A is N0A minus X equal N0A minus X. For reactant B, N0B minus B over AX. For the product C, 0 plus C over AX. For the product D, 0 plus D over AX, that means D over AX. This is the composition in terms of X, the general. Now, application. consider the equilibrium of synthesis of SO3 to SO2 plus O2 give to SO3. Consider X equal number of moles of SO2 reacted at equilibrium starting from a mixture of 0.5 mole of SO2 and 0.2 mole of O2. These are the initial number of moles of reactants. And X is the number of moles of SO2 reacted. The composition of the system at equilibrium in terms of X is, we write the equation, at T equals 0, initial number of moles 0.5 mole for SO2, 0.2 mole for O2, and 0 mole for product SO3 because we have no given for SO3 at the beginning. Variation for SO2 is X, it decreases X. Consider X number of mole of SO2 react, then SO2 react an amount decreases by an amount equal to minus X. For O2, we divide the stoichiometry of O2, which is 1, by the stoichiometry of SO2, which is 2, multiplied by X, then minus 1 over 2X. For SO3, we divide the stoichiometry of SO3, which is 2, by the stoichiometry of SO2, which is 2, 2 over 2 equal 1x plus 1x. At equilibrium, it remains 0.5 minus x for SO2, 0.2 minus 1 over 2x, and for SO3, 0 plus x equal x. This is the composition in moles in terms of x. From the concentration, the same as the number of moles, consider X, the concentration of reactant A disappears at equilibrium. The general equation, AA plus BB gives CC plus BD. At T equals 0, initial concentration of A, C0A, C0B for B, 0 for the product. Variation A decreased by amount X, B decreased by amount B over AX, C increases C over AX, and D increases D over AX. At equilibrium, C0A minus X, C0B minus B over AX, 0 plus C over AX, 0 plus D over AX. This is composition in terms of concentration. An example, consider the equilibrium of synthesis of NH3 ammonia, N2 plus CH2 give to NH3. Consider X, the concentration of N2 reacted at equilibrium starting from a mixture of 1 mole per liter of NO2 and 3 mole per liter of H2. The composition of the system at equilibrium in terms of X becomes N2 plus CH2 give to NH3, the equation. At equals 0, the initial concentration is 1 mole per liter for N2 and 3 mole per liter for H2. Variation minus X for N2, minus 3 over 1, 3X, plus for NH3, plus 2 over 1, stoichiometry is 1, plus 2 over 1, that means plus 2X. At equilibrium, 1 minus X, 3 minus 3X, 0 plus 2x, 2x. Application, 0.05 mole of SO2 and 0.1 mole of O2 gas are introduced into a flask of volume 1 liter at a constant temperature. The following equilibrium is established. SO2 plus half O2 give SO3. At equilibrium, the number of moles of SO3 is 0.01 mole. A. Determine the composition of the mixture in mole per liter at equilibrium. B. Calculate the constant of this equilibrium, Kc. Okay, we have 0.05 mole of SO2 and 0.1 mole of O2 initially, and at equilibrium 0.01 mole of SO3, and the volume equal 1 liter. Solution of application 4. we have SO2 N0 equals 0.05 mole plus O2 N0 equals 0.1 mole. At equilibrium, we obtain SO3 number of mole at equilibrium equal 0.01 mole. We should calculate the composition at equilibrium. We write the equation SO2 plus half O2 give SO3. At T equals 0.05 mole for SO2, 0.1 mole for O2, and 0 mole for SO3 because this given is at equilibrium, but at T equals 0 we have no SO3, the number of mole of SO3 equals 0. Variation at equilibrium. Consider X, number of mole of SO2 reacted, then SO2 decrease amount equal X. O2 decrease by an amount, we divide the stoichiometry of O2, which is half, by the stoichiometry of SO2, which is 1 half over 1 equal 1/2 multiplied by X. The product SO3 increase by an amount, we divide its stoichiometry, which is 1, by the stoichiometry of SO2, which is 1. 1 over 1 equal 1 multiplied by X. At equilibrium, (0.05 minus X), 0.1 minus half X, 0 plus X, X. But we should be given a value that permits us to calculate X, concentration of number of mole of SO2 at equilibrium, or number of mole of O2 at equilibrium, or number of mole of SO3 at equilibrium. The given at equilibrium is 4SO3. We are given the number of mole of SO3 at equilibrium equals 0.01, then which is equal to X, then X equals 0.01 mole. For SO2, 0.05 minus 0.01 equals 0.04 mole. For O2, 0.1 minus half times 0.01 equal 0.095 mole. Then this is the composition at equilibrium. B, Kc. Kc equal concentration of product SO3 over concentration of reactant SO2 times concentration of O2, each one raised by the to the power, which is the stoichiometric coefficient, SO3 1, SO2 1, O2 half. But the composition is in mole, in the expression of Kc should be in concentration mole per liter. Then we divide the number of mole by volume to transform it into concentration. Number of mole of SO3 equal concentration of SO3 equal number of mole SO3 over V over number of concentration SO2 equal NSO2 over V times concentration O2 NO2 over V power half equal, we simplify by V and V, same volume, it remains NSO3 in numerator over NSO2 in denominator times NO2 power half, and v power half is transposed into numerator, then times v power half. We replace each term by its value. Number of mole of SO3 equals 0.01 at equilibrium times volume 1 power half, which equal to 1, over NSO2 0.04 times number of mole of O2 0.095 power half. Using calculator you can find the answer. It should be without unit. Now, in terms of alpha, we denote by alpha the fraction of 1 mole of a reactant which reacts at equilibrium out of 1 mole of this reactant. That means if we start from 1 mole of a reactant, the number of mole reacted of this reactant is considered as alpha. Composition in mole. Consider alpha the degree of conversion of reactant A of the general reaction AA plus BB gives CC plus DD. Starting from initial number of mole of A, the quantity disappears at equilibrium is X. But if we start from 1 mole, the quantity disappeared at equilibrium is alpha. Then what is the relation between X and alpha? Starting from N0, the quantity disappeared is X. Starting from 1 mole, the quantity disappeared is alpha. Therefore, alpha equal 1 times X over N0, and that means X over N0A. And X equal N0A times alpha. Therefore, alpha by definition is the number of mole reacted of a reactant over initial number of mole of this reactant. Given the general equation AA plus BB gives CC plus DD, at t equals 0, the initial number of mole N0A and 0B 0, 0. Variation in terms of X, as we have seen in part composition in terms of X minus B over AX plus C over AX plus D over AX. Now we replace X by its value in terms of alpha, which is N0A alpha. Then minus X, that means minus N0A alpha, minus B over AX minus B over N0A alpha plus C over AX plus C over N0A alpha and plus D over AX plus D over N0A alpha. At equilibrium, N0A minus N0A alpha, N0B plus minus B over N0A alpha, C over N0A alpha, and D over N0A alpha. Example, consider the equilibrium of synthesis of SO3 and X is the number of moles of SO2 react at equilibrium starting from a mixture of 0.5 mole of SO2 and 0.2 mole of O2, and therefore alpha is the degree of conversion of SO2 into SO3. Then alpha equal number of mole of SO2 reacted, which is X, over initial number of mole of SO2. Then X equal N0 SO2 times alpha, N0 SO2 equal to 0.5, then X equals 0.5 alpha. Now, the composition in terms of alpha at equilibrium, in terms of alpha, not X. Two SO2 plus O2 gives to SO3. At T equals 0, 0.5 mole of SO2, 0.2 mole of O2, and 0 for SO3. Variation first in terms of X minus 1 over 2X, or plus 2 over 2, that means 1X. Now we replace X by 0.5 alpha, then minus 0.5 alpha, minus 0.25 alpha because 0.5 over 2 equals 0.25, and plus 0.5 alpha. At equilibrium, 0.5 minus 0.5 alpha, 0.2 minus 0.25 alpha, and 0 plus 0.5 alpha. Now, from the concentration, the same, consider X the concentration of reactant A disappears at equilibrium. Alpha degree of conversion of reactant A is the concentration reacted over the initial concentration X over C0A. Then X equals C0A times alpha. Given the general equation, A plus BB gives C plus D at T equals 0, C0A, C0B, 0, 0. Variation in terms of X minus B over AX plus C over AX plus D over AX. We replace X by C0A alpha minus C0A alpha minus B over A C0A alpha plus C over A C0A alpha plus D over A C0A alpha. At equilibrium, C0A minus C0A alpha, C0B minus B over A C0A alpha, 0 plus C over A C0A alpha, 0 plus B over A C0A alpha. Example, consider the equilibrium of synthesis of ammonia and H3. Consider X, the concentration of NN2 reacted at equilibrium starting from a mixture of 1 mole per liter of N2 and 3 mole per liter of H2. Alpha is concentration reacted over initial concentration of N2, X over C0 N2, then X equals C0 N2 alpha, which C0 N2 is 1 mole per liter, then X equals 1 alpha. The composition of in terms of alpha for the reaction N2 plus CH2 gives 1H3 at equals 0, 1 mole per liter, 3 mole per liter, 0. Variation minus X minus 3X plus 2X. We replace X by alpha minus 3 alpha plus 2 alpha. At equilibrium, 1 minus alpha, 3 minus 3 alpha, 0 plus 2 alpha. Application. First, remarks, in case of a decomposition or dissociation reaction, only one reactant. In a reaction when we have only one reactant is called decomposition or dissociation reaction. In this case, alpha is called degree of decomposition or degree of dissociation of this reactant. While in a reaction formed of 2 or more reactants, alpha is called degree of conversion. In case of one reactant, alpha is called degree of decomposition or of dissociation. In case of a complete reaction, alpha equals 1. In case of complete reaction, the limiting reactant disappears completely. Then alpha, which is number of mole reacted over initial number of mole. In case of complete reaction, the number of mole reacted equal to the initial number of mole. Over initial number of mole, then alpha equal 1. While in case of reversible reaction, number of mole reacted less than number of mole, initial number of mole, then the alpha is less than 1. X over N0, number of mole of reactant equal X, where X less than N0, because in reversible reaction, the limiting reactant did not or does not disappear completely at equilibrium. When any change displaces the equilibrium to the forward direction, alpha increases. Alpha is the conversion of a reactant to product. Then, when the reaction is more or the reaction proceeds in the forward direction, or the equilibrium is displaced in the forward direction, then alpha increase. While when any change displaces the equilibrium to the backward direction, if the equilibrium is displaced to the backward direction, then the conversion of reactants into product decreases, then alpha decreases. Now, application 5, the equilibrium of conversion of methane CH4 is established at a constant temperature according to the following reaction. CH4 plus H2O gives CO plus CH2, starting with an equimolar mixture consisting of 1 mole of each reactant, express 1 mole of methane and 1 mole of water. Expressed in terms of alpha, the degree of conversion of CH4, the composition in mole of the mixture at equilibrium. Deduce the expression of Kc in terms of alpha and V. V is the volume of the mixture in liter. Solution of application 5. We have CH4 N0 equal 1 mole and O2, the reactant is H2O, N0 equal 1 mole. Alpha is the degree of conversion of CH4, that means equal NCH4 reacted over N0CH4. That means it is X over 1, and 0 of CH4 is 1. Therefore, X equal alpha. The equation CH4 plus H2O give CO plus 3H2 at T equals 0, 1 mole of CH4, 1 mole of H2O, 0, 0. Variation in terms of X minus X plus X plus 3 over 1, that means 3X. We replace X by its value in terms of alpha, which equal alpha, minus alpha, plus 3 alpha. At equilibrium, 1 minus alpha, 0 plus alpha, 0 plus 3 alpha, 3 alpha. This is the composition at equilibrium in terms of alpha. This is part A. Part B, expression of Kc in terms of alpha and V. Kc equal concentration of CH4, CO, concentration of the product, CO times concentration of H2 power 3, our concentration of CH4 times concentration of H2O gas. The concentration is number of mole over volume, number of mole CO over V times number of mole H2 over V power 3. Our number of mole CH4 over V times number of mole H2O over V. Now, number of mole CO. First we simplify by V, and we have V power 3 and V, it remains V power 2. Then the V power 2, it change the color of the pen. Then we simplify by V and V, it remains V power 2. V power 2, it's transferred to a denominator. The expression, final expression, becomes NCO times NH2 power 3 over NCH4 times NH2O times V power 2. Now, number of mole CO equal alpha times number of mole H2 3 alpha power 3 over number of mole CH4 1 minus alpha and H2 also 1 minus alpha times V square equal 3 power 327 alpha times alpha power 3 alpha power 4 over 1 minus alpha times 1 minus alpha is 1 minus alpha power 2 and V power 2. This is the final expression of Kc in terms of alpha and V2. This is the end of part 7.